Welcome, everyone. This is our panel on smart panels and DC power for low power electrification. My name is Robert Nirenberg. I'll be your moderator today. I'm going to keep my comments very short because we are running just a shade low on time, but I would like to introduce Daniel Gerber. He is a research scientist at Lawrence Berkeley National Labs. His bachelor's is from MIT and his PhD is from UC Berkeley, both in electrical engineering. His postdoctoral work is focused on DC power distribution, and he was the technical lead on much of LBNL's studies in the efficiency and economics of DC power. Daniel has also developed several DC power and analysis tools and built up the LBNL DC testing lab. So welcome, Daniel. Thank you for joining us today, and I will turn it over to you.
Awesome. Thank you very much. And thank you, everybody, for your interest in this topic. Today, as Robert mentioned, I'll be talking about smart panels and DC power, and both of these are kind of fit as solutions for low power electrification. So what is electrification? I'm sure many of the previous presenters have kind of touched on this topic. Electrification is basically replacing gas loads with electric loads. So now you may think about your home. Do you have any gas loads? Many of you guys have a gas automobile, unless you've already upgraded to electric cars. But in addition, there's a lot more. My house actually has a gas furnace, a gas stove, gas water heating. Some people even have gas dryers. And so gas loads will always produce carbon emissions. Electric loads, however, if you power them from renewables, then they won't produce emissions. And so electrification is kind of this huge push in the United States and globally. So basically, the idea is to replace as many gas loads, if not all of them, with their electric equivalents. However, there is one problem. If you're going to be adding many electric loads to your home, you might run into some infrastructure problems. So this could be you have a 100 amp breaker panel and you need to upgrade that to a 200 amp panel, or it could be that the utility needs to make some upgrades to the feeder and the service drop. Now, these can actually be a very pernicious barrier, particularly for disadvantaged communities. Upgrading the breaker panel can cost anywhere between $2,000 to $4,000, depending on how much of the wiring needs to be moved around, how many of these different changes need to be made. And so that's kind of already unaffordable. Upgrading the service drop could be free, more or less. Sometimes the utility does it for you, particularly if you have overhead cable in this diagram. But there are some cases where the service upgrade might actually be pretty bad. And one of those cases is my own house. I have a 100 amp panel, but my service feeder runs under the street in front of me. So in order to upgrade that, the utility would have to rip up the street, kind of trench some new cable, and basically the bill that I have been looking at is $20,000 to $30,000. And so under any circumstance, these are very prohibitive cost barriers to many homeowners. And unless you're very motivated, most homeowners, even faced with a couple of $1,000s extra cost, would just get a new gas load when they need to replace their old gas load. So we need to solve this problem. And many researchers and people in industry, installers, are looking for ways to solve this. The whole avoiding the panel upgrade problem, or as we like to call it, low power electrification, has actually kind of turned into its own field of research. And this field of research it's a portfolio field, a portfolio of solutions. There's many different types of use cases or many different types of upgrades that might need to be done, many different types of electric loads that need to be added. And in each case, there might be one solution that works or another one or both. So it's not a one size fits all type of thing. One of the more popular solutions that people are currently looking at is, instead of having high powered loads, see if you can take a load and turn it into a low power plug load version. So one example is taking an oven and a cooktop range and turning that into a low power 120 volt plug that operates at 15 amps. These are all very promising, but the two solutions I want to present today are more on the infrastructure side within the building. One of the solutions I'd like to talk about is smart panels, and the other solution is DC power, and both of them have their time and place for when they're appropriate. So I'll first talk about smart panels. Smart panels are kind of part of a broader category of solutions I like to call power sharing devices. Power sharing device basically has one input and multiple outputs. And it basically ensures that the capacity at the input is not exceeded. So it can connect one output, both outputs, whatever it needs to do, as long as the input doesn't get over whatever the specification is. And so power sharing devices can be good because in many cases they are compliant with building codes. They won't worry electricians. They won't make people scared of fires. And so within this family, there's kind of 4 different categories of devices I'd like to talk about. There's smart panels, smart subpanels, smart splitters, and smart breakers. And these kind of go in a sort of hierarchy. So at the top of this hierarchy, we have smart panels. Now, smart panels, I will first say, do not avoid the panel upgrade. You have to buy a new panel, but they do avoid the feeder upgrade. So they're appropriate for cases in which the feeder upgrade is unaffordable, but the panel upgrade is okay. What is a smart panel? Well, it basically places a relay or some sort of remote shutoff at every single breaker, and it meters every single breaker. So with this monitoring and control capability, you can control very precisely what actually is being powered in the building. And so, example use case, if I were to replace my 100 amp panel with a smart panel, then I could program it to make sure that a new EV charger, a new induction range, a new water heater are not all turned on at the same time. And therefore, I can make sure that I don't go above the 100 amp capacity of my panel or of my feeder. And so, as I mentioned, you do need to do a panel upgrade. And these smart panels right now are kind of being offered at the $5,000 scale to buy one, but these companies think they could get it down to $3,000, which is still a lot, but is not arm-breakingly unaffordable. It will be a little more expensive than that if you need to get it installed as well. And so in many cases, these panels can also be programmed to coordinate the loads so that instead of kind of shutting them off directly, it can maybe coax the load into reducing its power consumption. But that's kind of in the works right now. It's not really a functionality you can get immediately. So let's say you have a slightly tighter budget, but you still want to have kind of a solid solution that can control many circuits. You can get a smart sub panel instead. These are being offered for half the price, so $1,500. And the smart sub panels kind of tap off of your existing breaker panel, and they can basically add monitoring and control to, in this case, for Lumen, up to 12 circuits. So now let's say that you have a really, really tight budget, but you only want to add one electric load at a time. So in a common example, you have a 30 amp circuit going to your garage that powers your dryer, and you want to get an electric vehicle that also can run off of that circuit. What you can do there is you can get a smart splitter. These appear in the $250 to $500 range. And smart splitters basically power one load or another. And they basically, in many cases, they have a relay that connects one or the other to power. Some of them, like the NeoChart shown here, can actually curtail the power going to the car, so you could run both at the same time. But for the most part, it's two loads, and as this diagram shows, the most typical example for these is two loads in a garage, like a dryer and an EV charger. So the final solution in this family of power sharing devices that I want to talk about is the smart breaker. Smart breaker is not really available yet as a low power electrification application, but I think it very well could be. Smart breakers are just like normal breakers, except they can be programmed to trip. They can receive a remote Wi-Fi signal telling them to trip. And what you could do with that is you could just pop out your normal breakers, put in a few smart breakers for the specific circuits that you want to control. And then if you kind of connect them to a controller, in theory, you should be able to have them ensure that they don't exceed a programmed current capacity. This is kind of a solution that's not available right now, might not even be code compliant, but I think it could be very promising. So we're currently looking into doing some research on smart breakers and seeing if they could be a very, very cheap alternative for low power electrification. So now I'd like to transition to the other topic of today, DC power distribution. And DC power is a very, very extensive field. It has a lot of applications, a lot of people are excited about it, but in today's presentation, I'd like to kind of get more specific on how DC power can help with the electrification problem. So for those of you who are not familiar, what is DC power distribution? Well, today, everything runs on AC. So from the power plant, AC, or alternating current, gets transferred over the power lines. It goes to the utility pole transformer and then gets sent directly into your home or building. And behind the walls, you also have alternating current, but at a lower voltage. The idea behind direct current or DC power distribution is to take some portion of the network I just described and make that DC rather than AC. And so the context that I've worked mostly in is the building, making all of the power distribution within the building DC, but then having AC come in from the utility. And so why is DC all of a sudden an exciting way to distribute power? Well, in the past, we primarily got power from coal-fired power plants or gas-fired plants, and those run pretty well on AC. But today, the most popular new way to power your building is localized renewable generation and battery storage. Pretty much all types of renewables, solar power, wind power, whatever, they're all natively DC. And batteries are also internally DC. In addition, most modern loads that you run today are DC as well. In the past, you might use incandescent lights, which could work great on AC, but today LEDs require DC. Any type of electronics requires DC. EV charging is another good example. It's basically a DC battery. And one load that many people might not think is actually also DC is any sort of motor load. So motor loads are required for the compressors in refrigerators, HVAC units, water heating, and all of these motor loads nowadays that are being created are DC as well. As shown below, we have a kind of block level topology of a variable speed brushless DC motor. And so you have the AC input, because everything hooks up to AC. You have to rectify it or convert it to DC, and then you have to have an inverter to convert it back to AC at a variable frequency. Now imagine if this load were connected to a DC circuit, you could get rid of this front end stage altogether. And so DC is very exciting for many reasons. We've done many past studies on this, and across the world, people are also looking into all of the reasons why DC may be beneficial. The one study that we've done most is into the efficiency benefits. In a previous project, I found that a DC building with solar and storage could save up to 12% the electricity compared to an AC building with equivalent solar storage and loads. This 12% savings is just from avoiding conversion loss. We also did a study on cost, which showed that even though DC components cost more today because of economy of scale, the energy cost or the electricity tariff that you save can actually offset this cost very quickly. Other things that people kind of are looking into are reliability and power quality. DC has better reliability and power quality than AC. And some other interesting things are, in many cases, you can it's easy to combine data and power in a DC line. And there's also the safety aspect, because many people like to distribute DC at 48 volts, and that's completely touch safe according to safety standards. So there are many benefits. However, as I mentioned, the benefit that I'm going to highlight today is that DC can help tremendously with the electrification problem. So in order to explain how that is the case, let me kind of explain what a building with AC and DC distribution would look like. Shown here, we have a building with AC distribution, and I've kind of color-coded it such that AC is red and DC is blue or teal. Every building in California needs to have some sort of net zero capability, so the easiest way to do that is with rooftop solar, shown here above. The solar power has to get converted to AC through what we call a maximum power point tracking inverter, or people usually refer to it as a string inverter or microinverter or whatever. You have your AC distribution bus. And now if you want to connect to battery storage, you need a battery inverter shown here on the right side. And at the bottom, as I mentioned before, all of your loads are natively DC. Therefore, you need to convert AC to DC for every single one of your loads. So you need this type of rectifier. Many of you might identify this, especially for the low voltage loads, as a wall adapter. These also show up as LED drivers. For the high voltage loads, they're usually packaged into the load, but you're all very well familiar with these types of rectifiers. So now let's look at the DC building, and this building is equivalent in every way except that the distribution is DC. So shown here, we distribute it at 380 volts DC, and that's kind of becoming a standard for typical high voltage DC distribution. We still have our solar input, and here we have a maximum power point tracking DC-DC converter. So we still need a converter to convert solar power to usable building distribution power, but these guys are very, very, very efficient. They have, typically they'll have 4 times less loss than the AC versions. Similarly here, you still do need a battery charge controller for interfacing the battery, but these guys also have, these are even better actually, they have 6 times less loss. And so you have a lot of high voltage DC loads, which if they're motor loads can just connect directly to the distribution. And in some cases, the low voltage loads like LEDs require an LED driver, or you might just need something to convert high voltage distribution into touch safe low voltage distribution. It all depends on what type of topology you want. The thing that I want to highlight though, is this unit right here. So in order to get grid power, which is AC, you need this grid tie inverter, or some people call it a gateway inverter, that is bidirectional and converts AC to DC or vice versa. This grid tie inverter is the reason why DC power can have a huge advantage for infrastructure upgrades, because the size of the circuit required, or the feeder size, is actually constrained by the power rating of this unit. let's say let's go back to my house for the example. I have a 100-amp feeder. Well, if I wanted to add a lot of AC loads, I'd require a panel upgrade. But if I were to have a DC network within my house, as long as this guy here is constrained to 100 amps, I'm good to go. I just connect it up. The utility doesn't care what happens behind the scenes. So now you could have lots of loads here whose total consumption might be way more than 100 amps. As long as you're powering it through solar storage, you'll be able to power the loads, and the utility simply just doesn't care. So now, of course, I wouldn't do this to my house. That would require huge retrofits and upgrades. But one example of where this could be useful is for new construction of electric vehicle charging. So let me kind of explain this using an example of a project that I'm currently working on. We want to electrify 4 buses in a school district. The California Energy Commission has kind of targeted these buses, or school buses in general, because they're heavy diesel emitters, or heavy carbon emitters, but they're also kind of bad for children's health and can kind of cause asthma. So electric buses, very easy target. The thing is that if we wanted to just put in 4 AC chargers and connect it to the grid, the utility would charge us $750,000 for the grid interconnection. I don't know how it's that expensive, but apparently, if we want to, well, I mean, the way that they do the calculation is they'll basically add up the maximum power draw of the 4 chargers plus the maximum power draw of any sort of battery connected to the system, plus the maximum power draw of the solar, which makes no sense because you'd think that the solar should count against the chargers, but it doesn't. And so infrastructure upgrades for charging depots, super expensive. Now, what we're doing instead is we're using a DC network to connect the generation, storage, and load assets. And this entire DC network is hiding behind a very, very small gateway inverter. This gateway inverter is going to be 20 kilowatts. So that's like half the power of a charger. And we're really only going to use it in case these 2 cannot power the buses. And so what it essentially boils down to is we don't need it to have an infrastructure upgrade at all because the utility is already providing 20 kilowatt service. And so this type of example is very useful for charging depots, but the same principle may well be applicable to buildings in the future or subsystems of buildings. Cool. Well, thank you everybody for participating in this presentation. Questions?
Thank you, Daniel. We've had a couple of questions in the Q&A that I kind of preemptively answered because I wasn't sure we were going to have time. But Ted Walensky asks, is the 120 volt 208 volt to DC 380 volt converter efficient, low losses?
So I think you must be asking about this grid tie inverter here. And I think from what I've seen, at least the data points that I've collected, this type of conversion is, when you have a bidirectional converter, it's maybe going to be around 93-94% efficient. If we go back to here, these string inverters have gotten pretty good. They're 96-97% efficient. The battery inverters here are maybe 92-93% efficient. And the grid tie inverter here is somewhere in between. And the whole point is, if you can properly size your solar storage and loads, then you can actually minimize the use of this altogether, because you can kind of just keep all of the generation, storage, and usage within the building. Cool. And I'm reading Alice's. Oh, okay, cool. That's actually, thank you, Alice. That's actually pretty interesting.
So Alice, for those of you who can't see it, Alice stated that the Whole Foods in Berkeley actually is effectively doing this and powering their lighting and refrigeration via DC system, and has been since the early 2000s. I'm going to go back to one of the questions. Seth asks, and I took a stab at this, so we'll find out if I was right. Are you suggesting having all components, LED lighting, computers, and motors, operate at the same DC voltage? LEDs and computer chips inherently operate at low voltage. Won't computers and LEDs still need a buck converter to lower the voltage with the associated losses?
Thanks a lot. Yeah, that's a very good question. So this diagram here is very much a simplification. LEDs will always need a converter or LED driver. And the reason for that, for those of you who are not familiar, LEDs are current controlled. So if you just connect it to a bus voltage, the bus voltage is voltage controlled. And in many cases, you'll blow up the LEDs. So you need a driver to kind of control the power that goes to the LEDs. DC LED drivers are more efficient, for sure, than AC LED drivers, but you definitely need them. As for electronics, the assumption that I kind of made here is that many types of electronics do have some sort of internal battery system. And I think for something like a laptop, you probably will, if you want to distribute at 48 volts, you will for sure need 48 volt to, let's say 12 volt or whatever your laptop battery likes to operate at, some sort of converter. The assumption that I made for this study was that internally, many types of electronics have an internal bus that kind of like the low power stuff, like the processor, the LED screen, they all generally tend to have their own internal buck converters that tap off of the bus. And so if you're powering it at a 48 volt bus, it is true that these converters might have to be bulkier. And so for electronics, this assumption might not be valid for everything like your phone or your laptop, or it might be valid for stuff like TV. And so that is a very good point.
Fantastic. Well, unfortunately, we're out of time, Daniel. So thank you very much for your presentation. It was very interesting and ties right in along with everything else we're doing. Thank you very much.
My pleasure. Thanks again, everybody.